and square root 2. If I think if anyone takes or take quantum physics, uh, these numbers are their amplitudes, their probability amplitudes. But I think you can go search it up if you want to know how does the probability amplitude looks like. So yeah, Hadamard gate in this Hilbert space, it maps to the computational basis states, which we defined in the first place, 0 and 1, into the superposition basis. So I'll explain here what this line of the maths equation means. So H acts on 0 qubit. And uh, how it acts is just like simple maths metric multiplication. So for 2 times 2 matrix time multiplied by the column vectors of 0 state, you get this. This is simplified. This is the simplified mass equation. So you can see that what this means is that this qubit, this added applied H operator qubit, is now in the state of 0 and 1. So what this I think, okay, 0 and 1 means that you can't think the qubit state now as just one face of the coin or just one bit. In the computer language, we just have 0 bit or just one bit. That's only one. No overlap or superposition state. But in quantum computing, in this qubit state, it has both states in this after this applied operator. Yeah, and this number here, 1 over square root 2, means the probability amplitude of these both state. Yeah, so uh when you times this 1 over square root 2 into the bracket, 0 state and 1 state, you get each has their own probability amplitude at 1 over square root 2. This is act on 0 state. How about 1 state? The 1 state is with minus sign here. So I think I don't have the whole mathematic equation shown here. So I guess you guys can try it on your own. Like 1 0 state is this, and this is 0 state. 1 state is just flipping the direction, the position of 1. So 1 will be at the bottom element. Yeah, and yeah, you guys can try it out afterwards. So okay, now I will try to show how H Hadamard gate, which I explained just now, is look how does it look like in Qiskit. Okay, I'll connect with the server. Yeah, yeah. Make sure Google Colab always connect here so that you can run your modules in your Google Colab. Okay, so here I have three library here. This is the basic Qiskit and Qiskit visualization, which helps you to draw the circuits, and I think block sphere also included in it. And Qiskit AER. AER means is online the simulator made by Qiskit. Oh, done already. Okay. All right. So we have successfully installed all the Qiskit package. So now here's the code for the next. Okay. As usual in Python, we always need to import the libraries. So from Qiskit, yeah, we have quantum register, classical register, and quantum circuit. So these three are also the basic codes library that needs to import before we try to create the circuit. Yeah, and this is Qiskit AER. So you can see the name here, AER simulator, which means simulator. Yeah. Okay, so next is quantum register. So in this bracket, what does it mean? One means that you are registering 1 qubit, and this QREG means just a name for you to label your quantum register. And I think this picture here you can see here, QREG. This is the name of your your qubit, your simulate qubit register here. And for this classical register is when we try to create circuit, we have to measure them. So by measuring them, they collapse into classical state. And we need something to record this classical state. So we use a classical register to record it. So here I registered one classical bit, and I name it as CREG. We are run this. Yeah, it's okay. So after defining all the register, you also need to define the quantum circuit. So the quantum circuit, in usual case, we always just define QC, and then this is the function quantum circuit. Remember that this is big C, and this is big R here. Yeah, and then the syntax inside this bracket is Q with C. The first variable will always be the quantum register, and the second variable is the classical register. Yes, Q and C I define here just here. Okay, so after registering the qubit and the classical bit, and also define our quantum circuit, now we are ready to draw our design our circuit. I would say design. So QC, which is the quantum circuit, then dot the Hadamard function. This is Hadamard gate. So here inside also, this is Q again, which is the quantum register you just defined just now, and 0. This 0 means that this is the first qubit, the index of the qubit. So if let's say you are registering, I try here, you are registering 3. I'll put this as 3 also. And yeah, oh, I cannot. Oh, sorry. Sorry. Okay, so yeah, you can see the difference here, right? So yeah, I registered 3 qubits, so that's why here we have 3 lines. And the index also show here, which is the first, second, and third, ordering by from up to down. And the classical register also labeled with number here, which means how many classical register is it. Okay, then yeah. Oh, the last line just drawing this circuit out, the function to draw this circuit out. And if you still remember from the 1.1 module, this output we can use some function in it. This one NPL shows the output like this, or we also can just another is what? Huh? Uh, I think just no input. Yeah, this is without NPL. The result without NPL. So everything okay? Is it clear? Okay, so I think I'll continue. All right, now the qubit is in quantum superposition state. Superposition state, remember, which is in 2 states here, 0 and 1, with their own probability amplitude. Okay, so here's the brief description. It can be either in state 0 or 1 until we measure. So when we measure it, it will collapse just one definite state. And we need to like I said just now, we need to register and record in the classical register. So here's another line of codes. Let me run first. Okay, it's successful. Yeah, again, these three library are the important library that will be used always. You will be used in creating quantum circuits, and this is a simulator also, which is important. And yeah, okay. So the difference here, the difference in here is that we have one more measure here, the measure function. Measure function also same like how quantum circuit here, Q and C. So Q means that you want to measure which qubit. I also can add uh, one or two here to specify which qubit I need to measure. But since here I didn't define, I just define one qubit, so I'll just put it here. And C will also be, you also can define here as two or maybe three to say that you measure it and then you record it in which register of uh, classical bit. Okay, so all here are the same. All right, now let's see how the state collapse when and then we observe through the output. So this is just a basic loop loop code. Okay, here this tree code is like a template for Qiskit to simulate and print out the output and store the output. So job here, AER simulator, then dot run. And QC is your quantum circuit name. And shots. Shots just one, yeah. Run with only one shot for here. You also can define it 100 or what. But in this case, I want to print this out. I'll just put it one here. And memory is also stated here. And then you dot result with the function here. So you will get the result, and then you get the memory of it. You dot get memory of it, and then you store this one. This line of code is you store at the outcome in this syntax here, which means it will come out as an yeah, it'll store in the outcome. Okay, so as you can see, the trial result we printed here, if you count clearly, 1, 2, 3, 4, 5, you can see there's only 5 1 and there's also only 5 0. So what does this mean? This means that our probability of getting 0 state and 1 state is 0.5 and 0.5 for each. So actually it also related to this equation. When you square this probability amplitude, you get 102 for each 0 state and 1 state. So to know the probability from this equation, you have to square it. And this is the result that we get, 102. Is it the same? Yes. So yeah, this is quantum. Okay, now this I try run with 10,000 times. Yeah. Then yeah, it's still the same. The template to run on the simulator. And yo, okay, so this is just a syntax for me to print this all out. And then yeah, we have this visualization library to help us import this histogram, and then we print it out here. So with 10,000 of shots, we can see that the result looks like this when we run on the simulator, when we execute on simulator. But okay, so in this is kind of a near perfect quantum computer, I would say, because the probability they are almost similar with 50 here and 49 here. But in real life situation, you really can't get 50-50. It's just that here is quite near perfect, but it's also count as 50-50 if you didn't care about the, I mean, yeah, it's just like that. So yeah, this is one state. When you see the x-axis, one state, we have 4,981 of the shots, we get zero state, and one state, we get these numbers of state. Okay, so, but our short brief here is that if you run on the real quantum computer, you might not get this result. This is just simulator, yeah, for your information. Okay, now, so, yeah, I skip this one. Okay, experiment two. So now, just now we are handling one Hadamard gate, and now we are going to play with two Hadamard gate. So again, we define the register, and our circuit. We first apply the Hadamard gate on the zero. Then we apply again on the second Hadamard gate on the qubit. Wait, let me run. Okay, yeah, it's the same. And then now we measure again. So recall that measure always collapse the state. So when we apply Hadamard gate, it's in one and zero and one state. And then when we measure, we collapse it into either one or zero. But here we have two Hadamard gates. So what's the result? Yeah. Here again the template. Then we print the count. And you can see the output here. It's just all the shots are zero state. So why this happens? This this outcome also can be calculated through mathematical notation. You can try here, h times the h and then times the zero or one. Then you see the output. You can try it later. And you know that why Hadamard gate returns the original states. Okay, now I have in this module just one question now. Because just now we all try in zero states. Yeah, zero states. So now you have to try it in one state. Your initial state is one. And to prepare that, here's the hint. Okay. Uh, I think that's all from my module. Any question? Right? Right. Cool. Cool. Okay. Uh, I think
So I think you can do question one, but while you're doing question one, actually I have one additional question that I just thought of just now. Um, okay. All right. Okay. I hope everyone also see this. So later on, you have like 1.5 hours of break. So okay. So while you're doing question one, you can also try to think of this additional question that I thought of just now. So over here, I show you how you can perform a Hadamard gate and then a CNOT gate to become the Bell state 00 plus 1, 1. So now create the gates in such a way that you transform from 00 to the other Bell state. And then you run it through the Qiskit and make sure that you get these states if you want to try. So design a quantum circuit in such a way that it transforms 00 to 1 over square root 2, 0, 1 plus 1, 0. So I think we can take for the lunch break now. While doing lunch, think of these questions. Okay, see you guys later. Yeah. So essentially, what you need to do is again to follow what was said previously. You see that when you perform, so over here, when you perform the halamat and then the CNOT gate. So basically over here at step 2, you already get the bell state. So what you need to add for step 3 is a bit break on the first qubit so that your step 3 basically becomes 1 0 plus 0 1. So which is exactly the same as what I asked over here. So that's essentially what you need to do for uh, in order for you to get the bell state with 0 1 and 1 0. So I guess with that in mind, we can go to the second session, which is on George-Schroeder algorithms. Okay, before we go into George-Schroeder algorithms, we need to know a little bit what kind of problems that George-Schroeder algorithm is trying to solve. Specifically, we first look at George algorithm. Uh, so before we go into that, we need to understand some terminologies. That is, what is a constant function or what is a balanced function? So if let's say f is a function that maps either 0 or 1 into 0 or 1, so then we can try to write down the function as f trying to map this particular set into this particular set. So we study specifically two possibilities. One is what we call as the constant function, whereby regardless of what is your input, you always get the same output. So that means that when you get 0 and when you get 1, regardless of your inputs, you always get the same output. It can be 0, it can be 1. So that's what we call as a constant function. So in table 2, I have the 0 constant function. Regardless of what is your x, you always get 0. And then the f1 constant function, regardless of what is your x, you always get 1. The second type of function that we are going to study is what we call as balance function, whereby the outcome has to be balanced in terms of 0 or 1. So if let's say you have one type of equation f2, whereby your input is 0 or 1, so it can either map to 1 0 or 0 1. So the number of zeros and the number of 1 that appear in the output always stays equal to each other. So that's what we call as the balance function. So the question that Josh algorithm tries to solve is how many times you need to ask or you need to operate on the function in order for you to identify whether it is a constant function or it is a balanced function. So maybe I can ask you guys as well. If I just give you a random function, I don't tell you whether this is a constant function or this is a balanced function. How many times you need to call the function before you know it is a constant or balanced? If your input is 2. 2 times, right? You cannot understand whether or not this is a constant or balance if you only call it one time. You need to call it two times to see which pattern it is. Okay? So now here comes the quantum so-called solution. Uh, the first step is for you to understand quantum oracle. Basically, the oracle is just a black box. You don't need to understand what is happening inside, but you need to know uh, what it does. So what it does is that it takes two party of the system, and then it take whatever input in the first quantum system, and then do a modular 2 addition to it, to the second part of the system. That's essentially how a quantum oracle works. So you can think of the oracle as this particular diagram. You don't understand what is happening in UF, but what you know is that you take two systems, which I call as the bipartite system. You take whatever input from the first system and you do the addition modulo 2 to the second system. And the first system remains the same. That's essentially that's essentially sorry. That's essentially what it does for um for this particular oracle. So the qubit, okay, I wouldn't say it is a qubit because later on it will be generalized. But basically, the X states is what we call as the input states, and the Y state is what we call as the auxiliary state. Okay, can you guys show that Y equation 33 is true? Equation 33 basically means that if you apply the oracle twice, you get back to the original state. Anyone wants to try why it is true? Yeah. No, you don't exactly know what happens, what is the quantum oracle. It can be unitary, it can be something else. But you basically get some of the ideas correct. So you can start to imagine because your fx is either 0 or 1, right? So let's imagine fx to be 0. If you perform the modular 2 sum, it changes nothing, right? When you sum to y, it becomes y again. You sum again to y, it becomes y again. So that's the first part of the proof. The second part is that if fx is equals to 1, when you sum it once, it becomes y plus 1. You sum it again because this is a modular 2 sum, so it becomes 0 again. It goes back to 1. Do you understand? Uh, okay. So yeah. So essentially, you can break this particular proof into two parts. If let's say fx equals to 0, then when you uh, do this, what you have is x, y, modulo sum 0. And it is just 0, just y, right? Because 0 adds nothing to it. So when you perform UF square, So this will be x. You do the modular sum twice. Uh, maybe so this actually does nothing. It will just gives you back y. So this is the first part. So now you assume that fx equals to 1. So when you perform it twice, the first time it will give you this. The second time when you apply UF, you get this. But because this is a modular 2 sum, so it basically returns back to 0. So that's why this is just x, y. Okay? Yes. I think I have, okay, I don't have slides. So what does it mean by addition modular 2? Basically, um, you can think of it as this particular truth table, 110. This is one way for you to identify what is the modular sum uh, 2. So that's how you prove equation 33. So another thing that you need to know before we go into the algorithm by itself is you need to understand what is step preparation. So essentially, later on, whatever algorithms that you see, most likely you will encounter a list of Hadamard gates acting on the zero zeros. Okay, so here I demonstrate for 2 qubits how it's going to look like. So let's break it down in a more detailed way. So let's say you have tensor product of Hadamard gates acting on the zero zeros, it becomes plus plus. I break this down into 1 over square root 2, 0 plus 1, and then I do the tensor product. So 1 over square root 2 multiplied with another 1 over square root 2, I get 1 over 2. And then you just do the tensor product accordingly. So you get 0, 0, 0, 1, 1, 0, and 1, 1. For us, the short form of writing this, the reason why I write in this way is because we can generalize it later. Essentially, the first part is just 1 over square root 2, 2 to the power of 2. The power of 2 part is basically depends on how many qubits you have. And then the summation, basically you take your x coming from 0 and 1. Um, okay, I might need to, okay, so over here, uh, this basically means that, okay, I might have some problems trying to going out of the switch. Yeah, never mind. This basically means you have 0, 0, 0, 1, 1, 0, and 1, 1. So in general, if let's say you see something like below, so this means you have um, n strings of zeros, and then you do all the possible permutation with 0 and 1 until you reach all the ones. So that's basically how this particular notation works. And then this x takes from this particular set. It means that this x by itself is you are summing from 0, 0, 0, 1, 1, 0, and 1, 1. So this is a very short form of way for us to write down this whole thing. And because I write it in this particular pattern, so you can generalize to, for instance, if you have n qubits with n Hadamard gates, you basically have this general form of equation. Okay, thank God. Finally, I can. So, this is what we call as state preparation. The reason why we call this state preparation is because basically it prepares your two qubit states into all the possible permutation of zeros and ones. And this is also what we call as a superposition. So all the possible bit strings for two bits, you can basically prepare by doing these operations. And this is quite important later on as well. So, okay, I have this actually. So what is modular 2 addition? Basically, you can call that as XOR as well. Um, Basically, it's that truth table that I've written down just now. So if let's say C can be 0 or 1, what is 0 modular 2 sum of C? No, C. Can you speak in terms of C? Sorry about that. It's just C, right? Right? Don't think so complicated. I mean, it's just C, okay? Okay, so if let's say C naught is 0, C1 is 1. What is 1 plus C naught? C1, 1 plus C1, C naught. Will the result change if C1, C naught becomes 1, C1 becomes 0? No. So, okay, so from these two statements, you say that 1 plus C naught is C1. 1 plus C1 is C naught. So the idea of C1 and C naught is basically one is you add one to the other. So now I'm asking if I interchange the value of C naught and C1, will this particular relationship change? No, right? Do you get what I'm trying to say? Because Pro Manager is like so confusing. No, I'm trying to give you some very general results regarding modular 2 sum because later on you need it. So essentially what I'm trying to say is, if let's say you assume one value to be 0, and then the other value is the other value that is not 0 because you either have 0 and 1. So essentially, um, this particular result does not change regardless of what is the value of C naught and C1. When you add one modular sum 1 to something, C naught, it will automatically become the other one. That's what I'm trying to say here. Okay. Okay. So now we we look into what is the algorithm for Gauss algorithm. So remember that the problem that is trying to solve is if I give you an unknown function, how are you going to determine that function is constant or balanced using quantum algorithms? So that is the question. So the problem is that uh, there is an unknown function. You need to decide either f is constant or balanced. So that is the problem that we are trying to solve. So we have seen that for classical way to identify it, you need to call the function two times. So now this is the quantum way of doing it. You only need to call it one time. Okay. So we go through the whole circuit step by step. Okay. So if you are doing this with Qiskit, usually the qubits over here, they how should I put it? They initialize in zero states. So in this case, if you see something like this, what you should do on the second qubit before you even begin the algorithm, you need to add a bit flip. Okay. So if you are doing it in Qiskit, either you initialize this specifically to the one state, otherwise, let's say you start from both zero, you just need to add the bit flip gates. So that's what I'm trying to say here. Not that one equal to x operates on zero. Okay, let us look at the first step. You begin with 0, 0, 1, and you try to add with Hadamard gates into the 0, 1 state. So what it will become is basically plus minus, and you expand the plus minus into this. So over here should be easy enough. It should be no problem. So now let's look at step two. Step two is our oracle. And what the oracle does is it takes the input of x and then modular sum to y. So this is the oracle, and this is the state from step one. So once you operate on this particular state, so basically it takes in um, your input of x from the first qubit, but I have not put in anything yet. So here I will just write fx for now. I have not really put in all the inputs. So already here we can sort of like make use of our first result that we derived just now. What is this? This is just fx, right? Okay. We cannot really simplify 1 plus fx for now. So we leave it there. So you can see we simplify this first part into fx. So that will be equation 36. So now let's look at this whole thing. So you assume that your fx gives you 0. So if fx equals to 0, so this will be 0. So 1 modular sum with 0, it is 1, right? So then it becomes 0 minus 1 divided by square root 2. So now if fx equals to 1, so then here you have 1, here you have 0. So it becomes 1 minus 0 divided by square root 2. And that is minus of 0 minus 1 divided by square root 2. Okay. So you see that 0 minus 1 divided by square root 2, they stays the same. The only difference is if fx equals to 1, you have an addition of minus sign. Can we simplify that? So what you can do is basically you can say that the whole thing on equation 36, the whole bracket, you can just write 0 minus 1 divided by square root 2 because this stays constant. And then you have a minus sign, which depends on the value of fx. If fx equals to 0, then basically there's no minus 1. If fx equals to 1, then you have a minus 1. So far, so good. So now we combine these very general results. So you can sort of like rewrite equation 36. So this is the original bracket. This is what I have simplified afterwards. Okay. So at this point, I have not applied whatever values is in during the first qubit. So this equality, I try to plug in all the values of the x inside. So when x equals to 0, you have minus 1 f0, 0, 0. So this is the first term. So now 0 multiplied with the second one, you have minus, minus, and then minus to the power of f0, 0, 1. And then you expand everything accordingly. Still makes sense? So now you can also regroup everything as well if you want to by putting this whole thing to the left-hand side. So the reason why I explain it to you is because you can check by yourself that equation 37 can be expanded into the equality on top as well. So you can basically move the minus 1 to the power of fx to the left side, but you need to make sure that the input here stays accordingly, like it stays true to the expansion. So then you can keep the right hand side, the rightmost bracket to be the same as before. So this is step 2. Step 2. So now let's look at step 3. You apply the Hadamard gate on the first qubit. So what it does is that basically over here it converts to plus, over here it converts to minus. And then you can explain the plus and minus again. So over here I directly multiply the square root 2 to the bottom. So it becomes 2 over here. Okay. Then the plus part is basically 0 plus 1, minus 1 is 0 minus 1. Is that okay? So now you have some terms that are the same. Like the zeros, you can collect them together. The ones, you can collect them together as well. So you collect the zeros and the ones together, you get an equation like this. Equation 38, basically. So why this is important? Because if if f is a constant function, then what will become of equation 38? Mhm. This is identity. So basically what it means is that you do nothing to the second qubit and you do hadamat to the first qubit. Okay, from equation 38, what you can say when f0 equals to f1? That is, f is a constant function. So if f is a constant function, let's say they are 0, then this will become 0. Over here, this is 1 minus 1. That means this term totally cancel off, right? Try to substitute f0 equals to f1 equals to 0. And you should see that the second term over here, they cancel off. You're only left with plus 0 and then 0 minus 1 divided by square root 2. So now you can try to see f0 equals to f1 equals to 1. You can also see that this particular term still cancel off. What you are left with is minus 0. So that's why you have equation 39 when f is a constant function. Do you need time to go through this? So what you can do now is to study what if f is a balanced function. So f0 not equals to f1, what will happen? I will not scroll down first. You can write down the states if you want to. Try to substitute different values of f0 and f1 and then understand what equation 38 will become when f is a balanced function.
Second qubit. No, second. First qubit of number one.
First qubit is?
First qubit one state. Plus minus.
Yeah. So again, what you can do is assume two conditions. The first one is, let's say f0 is 1. Sorry, let's say f0 is 0, f1 is 1. And then you substitute inside, see what happens. If let's say this is equals to 0, this is equals to 1. So you have 1 minus 1. So this whole thing totally cancels off, right? Huh? No? F naught is 0, so this is 1. Minus F1 is 1, so you have this 1. So you actually sums up. So so that's why you have plus 1 states with the, I will just write the short form minus states. So this is the first condition. The second condition is if let's say you have F0 equals to 1, F1 equals to 0, then you will notice that the first term still cancel off because over here, F0 is 1, F1 is 0. So you have minus 1 plus 1. So this one again cancel off. So now here you have F0 equals to 1, F1 equals to 0. So you have minus 1 minus 1. So that's why you have minus 1 minus. So combine it together, you get this one. Okay? So what does it mean? It means that by measuring the first qubit, you understand whether or not this is a constant function or balanced function. And how many times I call the oracle? I only call it once, right? So this is what we call as the quantum advantage. Something that quantum algorithms can perform better than classical algorithms. Okay? Okay, so far. For Dutch-Delta algorithms, because we try to generalize a lot of things, there will be a lot more mathematics involved. Yeah.
For the definition of X, is it the state of the first qubit?
Fx takes whatever value from the first qubit and then compute a number to it.
The computation is C or is it?
Okay. The definition of oracle is that you basically don't need to understand what is happening inside the black box. You just need to know that you have some black box that takes in whatever input from the first qubit and then do the modular sum to the second qubit. So in a sense, is this algorithm useful? What do you think? Do you think this algorithm is useful? Or this problem, do you think is it useful? It's a manufactured problem to show that quantum algorithms can perform certain tasks better than classical algorithms. That's why you maybe you feel like, okay, what is the point of this, right? But this is one of the proof that quantum algorithm can perform something better than classical ones. Okay, maybe, okay, this is quite a long one. So before we go into Dodge-Jozsa algorithm, it is useful to generalize a lot more results, particularly on this equation. If you have a list of Hadamard gates that acts on whatever states, X states. So what it will give you from the output is that you have a -1, and then you have a sort of like a dot product, but it's actually not a dot product. The definition of this particular dot product is that you sum up all the independent elements with the modular 2 sum. Okay. You will see why this is important later on. So we will look into some examples. Let's go back to 1 qubit. So, okay, I will not prove that this is how this is coming into it, but you will just see some examples. So, for instance, if let's say you start with 1 qubit, the zero state, you know that this will become the plus state, right? So now you try to apply the results. So n equals to 1. So you have 1 over square root 2. And then the sum is basically from 0 to 2 to the power of n minus 1. So n is basically 1. So meaning that whatever you sum is y equals to 0 to 1. And then you have minus 1. So this is basically just 0 uh, multiplied with, what's that? So when your y is 0, okay, maybe, so this is the first one. Sorry. This is the first one. And then you have the second one. So this is what happens when you expand the summation. So remember that one of the term coming from the left-hand side, which is 0, the other one comes from the index of your summation. So that's why it becomes 0 plus 1 over here. When you do the same expansion, because this is minus 1, 1 multiplied with 0 gets 0. So that's why you get 1 over square root 2, 0 minus 1. Okay, example, find that using the equation. So if you follow the equation, then basically you know that n equals to 2. So you have 1 over 2. The summation is through 0, 0, 0, 1, 1, 0, and 1, 1. And then you have minus sign multiply with sort of like the vector sum of x dot y, and then you have y. So for 0, 0, basically you get 1 multiplied with 0 plus 0 multiplied with 0. So you get plus sign. Second one, you still get a plus sign. The third one, you get a minus sign. The fourth one, you get a minus sign. Is it okay?
Why is given to then x times y will be uh, 1, right?
If you follow this equation, because x is basically 1, 0.
Y is the
Uh-huh.
so the uh,
So let's say this is x1, this is x2. So x1, y1, x2, y2.
oh
Yeah. So you can sort of verify this because this is not a very difficult multiplication. So essentially, you know that h tensor with h, when you add on 1, 0, it gives you minus plus, right? So minus plus minus basically is 0 minus 1 divided by square root 2, 0 plus 1 divided by square root 2. So you perform the multiplication to see whether or not you get this particular result. If you get that result, then basically you are right. So 0, 0, 0, 1. So 1, 0, and 1, 1 is negative. So meaning that this expansion is the same as the one that you did for the equation. So do you understand how equation 41 works? Perfectly clear? Okay, any question on equation 41? Uh-huh.
let's say it's 1, so x1 1 x go
Yes.
and y1 is
So y is a little bit confusing when you write in this summation, but essentially it will be clearer if you instead perform the summation in this manner. So you know that your summation of y has to be 0, 0, 0, 1, 1, 0, and 1, 1, right? So when your y is 0, 0, it means that your y1 equals to 0, y2 equals to 0. When 0, 1, this is y1 equals to 0, y2 equals to 1. Here will be y1 equals to 1, y2 equals to 0, plus 1 will be both equals to 1. Then you perform this particular multiplication.
the summation is not y to 1. Create equation 41. Yeah.
Okay, okay, I have to admit this is a bit confusing because I need this thing. But essentially, the real summation is that it is still y summing from 0 um, up to 2 to the power n minus 1. Sorry, the 1 is a big term. But when you do the how do I say? When you do the summation, you actually convert it to binaries. So 0, 0, 0, 1, 1, 0, and 1, 1. This is the binary representation of the number from 0 to 2 to the power n minus 1. Okay. A little bit confusing. And that's why I show you one example to show you exactly how it is being done. So is that okay?
To only calculate uh, the odd one now, the one that doesn't have a pen. Because every time we apply it twice, that is going to revert back to the original value.
Oh,
So
okay. I think you get confused with this.
yeah,
So this basically means you apply twice on the same qubit. Whereas if you have this, it means that you take note of this tensor. This is a short notation as well. You apply on two qubits in a parallel kind of setting. So the right side is the parallel, the left side is series. So what this equation is about is when you apply it in parallel. So you cannot apply that condition thing. Okay, we can go a little bit slower over here because I know I'm doing the slides, so I know exactly how difficult it is. Okay, let's try to push a little bit further. Basically, we want to derive some very general equation from what we have for Josh algorithm, so that when we go into Josh algorithm, we have a general form that we can use. Okay, so remember equation 38 is this whole thing. So can we use equation 41, which is the equation that we introduced into equation 38? Okay, how should I think? Okay, so essentially, right, remember that the last part you have the Hadamat gate. Over here. Okay. I think it's between the end of step 2 and then before the step 3. I think it's over here. Is it? Let me check. Yeah, it's over here. So this equation is exactly coming from here when we begin our step 3. Okay. So then over here, the first equation, we simplify it back to the summation form. Of course, the 1 over square root 2 is just a constant, so you can move out. So when you do the simplification, essentially you can write into this particular summation. So if you cannot see through the summation, what you can do is to see if you can expand into it. So basically, if your x equals to 0, then you have minus 1 f 0, and then the 0 state. And then when your x equals to 1, you have minus 1 f1 to 1 state. So you know that this particular summation can be expanded into the, the one on top. Okay, so this is fine. So now we try to apply this Hadamard gate into here using equation 41. Okay, the reason is not uh, obvious right now, but you'll see why we want to do that later on. So how can we generalize this using that equation? So remember that just now, okay, so this is the left side. So the left side, I just move out. So it's the same thing, right? The summation. So what is the function of this h acting on this whole thing? Basically, it gives you the equation on the right, the summation on the right. So basically, the summation on the right is exactly the same as equation 41 for 1 cubic. So you have the summation of all y from 0 to 1 because it's just a 1 cubic. And then you have minus 1 x multiplied with y in the y state. If you cannot see this particular summation, you can go back to here and you can see that this is exactly the same equation. Summation y from 0 to 1, you have minus 1. Of course, here, because your x equals to 0, I directly apply 0. If this is your x state, then this will become x, right? So the whole summation over here is exactly the same as the one before I showed you. Okay? So finally, okay, another thing is that over here you have 1 over square root 2. So this has moved out as well. So notice that from here you have 1 over square root 2. It changes to 1 over 2. So now the last step is to combine the summation and minus 1 together. So when you combine it together, you have summation of x from 0 to 1 and then y from 0 to 1. And your minus sign, minus 1, basically fx, you sum them up. So it's just a sum of x dot y. This is a multiplication, by the way. So this whole term multiplied with this, that's why your index sum together. So you have a job right now trying to use equation 42 to expand back to 38, which is given by below. Make sure that it works. I think I will give you guys like 20 minutes to do it and maybe some rest time as well.
Scroll up.
Huh?
Scroll
Scroll up.
up.
Is that okay?
You want some?
Yeah, it's fine. Okay, thank you. Huh. I hope everyone can do this. Yeah, basically you just apply equation 42 and then just expand it, right? And you should be able to get the equation as follows. So yeah, so far we look at George algorithm. It tries to solve a function, like try to identify whether or not a function is a constant or a balanced function. And specifically speaking, what type of function? For George algorithm, the function is trying to map a function with either 0 or 1 as input and then gives you either 0 or 1 as output. So what George algorithm does is to generalize this to whatever input with like n inputs, and then it gives you one output, either 0 or 1. So what would be the example? So if let's say you have n equals to 2 in this case, in this particular example, so this is your x, so you either have 0, 0, 0, 1, 1, 0, 1, 1. So what will be your fx? If it is a balanced function, it will be 0, 0, 1, 1, for example. Okay. Or it can be everything 0 if it is a constant function. So for this specific example, n equals to 2, if it is a classical algorithm, how many times should I call the function to know that whether or not this is a constant or balanced function? One time. Four times. Four. Three. Why three? Why four?
you can verify whether it's constant function. But at the same time, if you have three, you can also identify whether it's the fx, the second column. Maybe not the value.
So everyone agrees it's a 3 times?
Maybe it's only balance or constant.
Yeah, it's always only either constant or balance. So basically 3 times is what we call as the worst case scenario, because if let's say the first time you call is 0, second time you call is 1, then immediately you know that this is a balanced function. But the worst case scenario is the first 2 calls you get 0. You need a third call to identify whether or not this is constant or balanced. In general, if let's say I have n input, how many times should I call the function for a classical algorithm? So now if let's say this is n, how many times should I call the function?
And over 2.
N over 2 plus 1.
I guess because now here is n.
So you put it 2 together. What? And square over 2 plus 1.
2 to the n over
2 to the n
2 to the n
minus 1.
Yeah.
2
Something like this. I guess.
to the n minus 1 plus 1.
Something like this.
I mean, you apply 2, you apply the current example. If you get 3, then it might be right? So the answer is 2 to the power of n minus 1 plus 1. Correct? Everyone agrees? Yeah, this is the worst case scenario for n numbers. Do you get why? So basically for n equals to 2 in this case, you take the total number of possible entries, which is 2 to the power n, 2 to the power 2 in this case. You divide by 2, and then you add 1, right? So that's why you have 2 to the power of n minus 1 plus 1. Everyone understand the logic? Okay. So this is the worst so-called worst case scenario if you have a classical query system. You need to call this many times in order for you to identify whether or not the function is constant or balanced. So now we look at the quantum algorithm. You will notice that everything stays more or less the same, except that your input now becomes 0, 0, meaning it is a 2-qubit state. You still have the ancillary states as 1. And then over here, you have tensor product of Hadamard gates. And then over here, you have tensor product of Hadamard gates as well. So everything is more or less the same, except that you put in more Hadamard gates on the input states and put in more Hadamard gates on the output states. Okay, so now let's look again on each of the steps, what is happening. So the first step, nothing strange. It's just tensor product of 2 Hadamards. Again, you tensor with the third one. The reason why I write like this is because I want to differentiate the third Hadamard acting on the ancillary state. The first 2 acting on my input states. Okay, so this part acting on the input states is the state preparation. And once you do that, remember when we have the step preparation equation, we basically have this equation. I hope you still remember that from the very first here, step preparation. Okay, so remember that whenever you see a structure like this, a bunch of zero states, and then you apply with a bunch of Hadamard gates, um, like in parallel, that's basically trying to prepare your quantum states into a superposition of everything so that you can use the oracle to do something that you want to do. This is quite common even for the later quantum algorithms. So this part is the state preparation. And then the Hadamard gate acting on the ancillary state gives you the minor state, which you can expand into that. So that is your first step. So the second step, you use the oracle, you call the oracle once. So this is where things started to get a little bit complicated because, okay, the oracle will, okay. So first thing first, what we have learned from Deutsch algorithm, we essentially know that as long as after you do the first Hadamard gate, the ancillary state basically does not change, right? Whatever you are trying to do, you are just introducing a certain phase into the first qubit. So from now on, whatever I'm trying to write, I will not write the last part because this will just waste my space. Okay, I will just focus on the first part. So what is the effect of having the oracle on uh, these complete states? It will just introduce this thing, right? If you look at the George algorithm, where's that? Yeah, step 2, you introduce the oracle into this is your input state, this is your ancillary state. You find that the result is that you only introduce the -1 phase to the first qubit, while your second qubit has nothing changed. So I'm trying to generalize the effect of this by putting on this particular summation. So having the oracle acting on your quantum state on the after the first step, it basically just introduces a phase -1 to the power fx onto your state. So here I mentioned, like I said, the ancillary qubit is not important. So for the step 3, we will just look at the input states. So now step 3, we have 2 Hadamard gates acting on this state. Okay, so this is where we make use of these results. Equation 41. You have a tensor product of Hadamard gates acting on some states. It gives you another state with a -1 x dot y as your phase. So you try to do that over here. So over here, I expand everything just to show you what are the steps involved for the input states. But you can directly make use of the equation. I will probably not go through all the expansion because basically over here, you just try to expand the summation whereby your x can be 0, 0, 0, 1, 1, 0, and 1, 1. So after the expansion, then you apply Hadamard gate on the first qubit and the second qubit. So you get plus, 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 minus, minus, plus, and minus, minus. And then you expand again the plus and minus into either either 0 plus 1 divided by square root 2 or 0 minus 1 divided by square root 2. So because you have 2 qubits over here, so you need to do the expansion twice. So for instance, from the first one, plus plus, what you will have is 0 plus 1, answer with 0 plus 1, right? So that's why you have 0, 0, 0, 1, 1, 0, and 1, 1. So if you look at, for instance, over here, this will be minus plus. So you have 0 minus 1, cancel with 1, 0 plus 1. Sorry, this should be here. So you just do the expansion accordingly, and you should be able to get equation 45. Do you want to do the verification? So the expansion is what I did. Now you just need to verify that the summation actually gives you exactly the one that I expanded. I will probably skip this if everyone agrees, but trust me, I've done this. I think I know this is true. I've done this calculation as this is true basically. Okay. Now, what is the implication of this particular equation? Again, you do uh the whole if let's say f is a constant function, what will happen? If let's say f is a balanced function, what will happen? So let's start with, let's say f is a constant function. What will happen to the equation? First of all, you look at each line. What do you notice? What is different from the 0, 0 states and the rest? For the 0, 0 state, everything is positive. But for the rest of the states, you always have a balance, positive and negatives, right? So what does that mean? If it is a constant function, it will be only 0, 0 states will win, right? Will survive, right? Okay. So what will happen if it is a balanced function? The 0, 0 state will be destroyed, right? It will be not happening, right? Because if it is a balanced function, basically for 0, 0 state, two of them will be positive, two of them will be negative. I don't really care about 0, 1, 1, 0, and 1, 1 in this case. Okay. So if the function is constant, because of what we call as the constructive interference, then you will only get 0, 0 state. If you perform the measurement and you find that you don't get 0, 0 state at all, then it is a balanced function. So this whole phenomena is not just for 2 qubits. In fact, for n number of qubits, you always can construct this particular algorithm, and you just need one oracle call. Okay. Yeah, I think that's all for this shows algorithm. Any questions from you guys?
Why do we say the period is here? Why do we say it's the period?
Because it's sort of like how it sort of like mimics how the constructive and destructive interference in this case.
Is there like programs on it, or is it just the third period?
Okay, when you perform the state preparation, you basically try to prepare all the possible scenarios in one go in superposition. So in that case, you can regard that as your wave point. Yeah. You try to explore all the possible solutions at once by using one oracle call.
So yeah, maybe to test the exist or not. So
Yeah. So for those Schwarzer algorithm, you basically just need to test whether or not 00 exists. If 00 exists with probability 1, then it is a constant function. If 00 does not exist, then it is a balanced function.
we who can measure the big sign. So we can have a proof that only measures the
Okay. Like, okay, just now, during the Qiskit sort of like tutorial, so you notice that you have like the quantum register and the classical register. The classical register is for you to perform the measurement and then record down what is your value. And just now you have seen all these counts, right? So essentially, what you are doing for like what's that? For at least for simulation purposes, you can measure each of the qubits and then record down what are the counts. So if let's say you have 3 qubits, usually the measurement will look like you have 0, 0, 0, 0, 0, 1 up until 1, 1, 1. And then you get like the counting. So that's how, at least for simulation purposes, that's how you would see what are the states that you are in. So if let's say 00 gets every count, then basically that means you get a constant function.
Just to make so Josh was algorithm basically make take a better way find whether f is constant or balanced by just by looking for the 0, 0, 0 or n times. Compared to classical, you have to check everything.
Classically, the best known way for you to identify is do the 2 to the power of n minus 1 plus 1 queries of the function. But for quantum, as long as you are able to do the state preparation, meaning put all the possible, meaning testing all the possibilities at once, the superposition thing, then you just need to call the oracle once and then do the measurement for 00. Then you know whether it is a constant or balanced function. Yeah. Yeah. Yeah.
So yeah, so if like 00 other so that is if 00 coming out of it,
Yeah, basically you just set the all the 0000 state, right? If it exists, it's constant. If it doesn't exist, it's balanced. You don't need to look at other states. Yeah. Yeah. You basically check the probability. Is there any other question?
For n equals to 2, right?
Yeah.
So n is equal to 3.
Okay, you can take this as homework and expand everything yourself. Yeah, please do that. I root for you.
Would there be like interference
Huh?
in n3 when the book?
Sorry.
Would there be like this interference pattern still?
Theoretically speaking, it works for n for any number n. Yeah. You just measure all the 0, 0, 0, 0 state. If it exists, it's constant. If it doesn't exist, it's balanced. Yeah. But if you don't believe it, please expand it at home. I root for you. Okay. If there's no other questions, maybe we can switch to some demo from Qiskit. No.
First time.
So we should welcome our C Quantathon and what? High Ventures hackathon participants. No. Actually, she's going to demo Josh Joseph.
That's why go back to the slide hackathon.
Maybe you do the demo first. Then if you want to.
Slide.
They want to introduce.
Just introduce. Sorry. Which hackathon is like? No, I mean the this morning flow.
This is the one.
Canvas. You after you are picture. Yeah. I just after you are this
Oh.
okay. You know all the helpers.
Okay. Prof, maybe you use the one and speak a bit.
Okay, so I just want to introduce more. Where is the picture? Where is it? You don't put. Where is it already?
No, don't show.
I have to explain. Yeah, so then they know that you already have the track record. Yeah. Can
Don't press anything.
okay.
Because okay, they did not show that.
Why? On high page. Why? Yeah.
Why?
Because it's a very I mean very good that you can win something. Yeah, to make the yeah. So we can do it.
That's why at the back.
Some of them is on the back. You see all these things? This one is the first one in Thailand. Yeah, I also joined as a mentor. Dr. Chong was like, actually, that's why I involved more events with the quantum computing. Yeah. So if you see that, maybe you introduce yourself. Yeah.
Yes.
Hi everyone, my name is Hui En. So I'm currently in my third year, studying physics at UM-UPM. So yeah, on August. Previously, I've been to Thailand for this Sea Quantathon. So yeah, our team managed to won the second runner-up, which is the third place. So after that, I think a few days ago, the team back there, so they all was one of the top 10 finalists in Thai Gen Q hackathon, also a quantum hackathon in Singapore just a few days ago. Yeah, they fought against a lot of masters and PhD students. So it was really, yeah, even the teams participated there have like I think 4 quantum startups already. So basically, because they didn't have any age restrictions, so being a top 10 finalist is really like wow, amazing.
Been new opportunities to meet like a new mentor or another supervisor, different place of the world. You like really join kind of event. At first, everyone scared also, right? Like what is this? He never experienced this one. Third year only. Something. Yeah. Then we get more already. We send another 5. Then also in top finalists. It's not like top 10 finalists among like 25 or 30.
Yeah, 20 something.
Consider very good because of good mentor.
Oh, no.
For now, we further we share something that maybe practical for you to do.
Yeah.
I think Google Colab or use
Yeah.
yeah.
So I believe everyone can do.
Is it presenting the group over here?
It's still presenting.
It's presenting. Do you like handle questions from Zoom? Or
Unfortunately, I can't.
you cannot? Anyone else handling?
It's very intense. Really similar. Don't sleep one. Building the class, how to solve the problem. Very fun. Yeah, you should try one. Yeah.
Wait, why?
Friend, different group, interact with the mentor. Yeah, directly. Yeah.
This one should have opened it first.
So next time, enjoy. I don't know which one is the next part. Actually, the first one, we join Sanadu. Sanadu is also like another pet.
Okay, it works. That shows up. Yep.
They already have these modules in hand.
So.
Building the supercomputing as a quantum computing. And they use the penny lane to make a tutorial. Maybe tomorrow I show you a little bit.
So the time is until 4. Okay.
So the first one we got quantum chemistry group. Among quantum meeting. Not that bad. More than 1,000. Like,
She's so copy through my they have to participate.
okay.
Okay.
So this one, no.
So we'll okay, so just okay, I'll introduce myself a little bit. So my name is Hui En. So I'll be the coordinator for the Dosh-Joza algorithms module. So I'm sure everyone have this module in hand already. Is it? You guys managed to open this module? So yeah, and I'm sure you have been introduced to Dash problem, which is a Boolean function. We have a Boolean function which takes the inputs of either 0 or 1 and maps to either 0 or 1. And we say the function is balanced if if f0 is not equals to f1, meaning if you input 0 and when you input 1, the results come out is different. So we say that this function is balanced, and it's constant if whatever you input, the function will maps to like a certain value, for example, 0 or 1. Okay, so but for now, we don't know whether this Boolean function is constant or balanced. Then we can use Dash algorithm to kind of query this oracle to know that whether it is constant or balanced. So the steps are basically like this. I'm sure you have gone through the mathematical part just now. So I kind of just list out the steps over here. So what you do in Qiskit is that you follow the steps. So you can look at my example one. Okay, so I've defined an oracle right here. So okay, although you can see the code here, but just imagine that you don't know what this code is happening. So it's just like a random oracle that you are given to. So after that, you have to implement the Dosh algorithm to determine whether this given oracle corresponds to a constant or balanced function. So we start by importing the values. Okay, then we create a 2-qubit and 1 classical bit circuit. So 2 qubits, basically we have 1 input qubit and 1 output qubit. So together 2 qubit. 1 classical bit is used to store the measurement from our input qubit. So input, output, yeah, sorry, output qubit. So then after we create this circuit, we can start implementing all the steps stated earlier, which is here. So we start by preparing the second qubit to the minor state, which is applying X and Hadamard gate. So we apply a X gate to flip. So initially everything is in 0 state, right? Okay, everything is both of the qubits are in 0 state. So when you apply X gate to the second qubit, it becomes in the 1 state. Then after that, you apply H gate. So basically, you will have the minor state there. Okay. Then after that, the second state is to apply Hadamard gate to the first qubit. So we will do that in Qiskit. Okay. So I'm sure in the morning session, they have sort of introduced you to what are the basic syntax in Qiskit, right? So I'm sure you have no problem, but if you do have problem with the syntax, you can always Google up Qiskit documentation from IBM, okay? So next, apply Hadamard gate to both qubits. After that, we add the oracle. So the oracle is our is in a unitary matrix, okay? So because we have defined over here, so the function's name is oracle. Okay, so it kind of like uses QC dash compose oracle in place true. So this line here basically adds the oracle. So when you see, you can see there's like a barrier on top and a barrier below. And when you look at the circuit, it's just like this barrier and this barrier. It's not necessary, but it's like, what happened? Okay, but it's easier to visualize when you have the barriers over there. How do you? Okay, so yeah, it's just for better visualization. Then after that, we continue implementing the Dash algorithm. So we apply Hadamard to the first qubit. Then after that, we measure the first qubit. When you see the syntax is like 0, 0, it means that we measure the first qubit. The first 0 means that we measure the first qubit. The second 0 means that we measure already. We store our measurement result in the first classical qubit. Remember we have 1 qubit, 2 qubits and 1 classical bit. So the second 0 means that we store the result in our first classical bit. That's the meaning. So it's kind of like a mapping. Okay, then we draw the circuit diagram for better visualization. So the center here, you can see it's a C0 gate, right? That's basically the oracle. Okay, but I told you guys to like just forget about that, you know, the oracle, because we just want to test, right? Test the Dosh algorithm. So after that, when we have all these, then we can start to run a job on a simulator. So when we write sampler sim equals to AI sampler, this one is actually we are creating a simulator object in Qiskit, which allows you to actually run this whole quantum algorithm on your computer instead of running on a quantum computer. So it's basically a quantum simulator. Okay, so the job here is to just run the circuit. So I just put like for 1,000 times. Shorts is like how many times you run it, because you know quantum algorithms are probabilistic, right? So sometimes you have to run it a lot of times, but I think for Dosh algorithm, even though you run it like one time, you can get the result, but it's okay. You can you can try modifying the number of shots to 1 or maybe 100 or whatever you like and see the results. Then we store the job result in the RES result. Then after that, we can analyze the result. So basically, the counts means like we get the counts of like how many zeros, how many ones. Then after that, we can kind of write like if else. So if the result is 1, then it's a balanced function. If not, means 0, is a constant function. So when you run this, you should get like the number 1 for 1,000 times, because our shorts is 1,000 for now. But if you modify here, you should get a different value here. So for this C0 gate oracle, basically it's a balanced function. Okay. Any questions? So basically, this is how you implement Dosh algorithm in Qiskit. No? Okay. So this is an example provided here. Then next, after that, we can kind of like proceed with the generalization for the Dosh algorithm, which is to take Dosh algorithm, turn it into Dosh-Jozsa algorithm. So Dosh-Jozsa algorithm basically means that you have a function, 0, which takes into n number of inputs of either 0 and 1, then maps to one output only. So the one output is either 0 or 1. Okay, so you also have the constant or balance function using this Dosh-Jozsa problem. Okay, so I've gave like examples of like a constant and a balance function. So let's take like, for example, now you have 4 inputs because n, right? For example, n equals to 4. So if the first table over here, the up here, is a constant function, because no matter what your input is in, I think it's 8 input, sorry. Okay, no matter how many what you input, the output is always 0. But for the balance function, you can see half of the output is 0, half of the output is 1. This is what you call a balance function. So the Dosh-Jozsa problem is, given this function as an oracle, you have to decide whether it's constant or balanced. Okay, so Dosh-Jozsa algorithm basically is the steps are the same as Dosh algorithm, but you just have n qubits instead of 1 qubit. So we construct a circuit with n plus 1 qubit instead of 2 qubit. Just now we construct, if you recall, when we have like 1 input, we have 2 qubit circuit. So we have n inputs, we will have n plus 1 qubit. So we need 1 extra qubit for the output as the output qubit. So we have n inputs plus 1 output qubit. That's why we have n plus 1. Okay. So I have the oracle over here. Then the rest is just the same with the basically the same steps with Dosh algorithm. So you set all the n plus 1 qubit state to minus state, which is the last qubit. N plus 1 qubit means, for example, if you have 5 qubits, you have to set the fifth qubit to the minus state. You only set the last qubit to the minus state by applying X and H gate. Then you apply Hadamard gates to the first n qubits. Can I write something? Yeah, have to switch, is it?
These settings up first. Use it here. Oh, wait, switch.
How do I refer back to the?
Yeah, you.
Oh,
I have to do
okay,
that.
okay. So just now we were saying, let's take, for example, okay, my question is like we have 4 inputs qubit. So let's take 4 for example. So you have qubit 1, 2, 3, 4, 5. This one is the n plus 1 qubit. So you set this one to minus state. Then the first 4, apply Hadamard. Okay? Okay. Back to the. Okay, so after that, you apply the oracle, just like just now how we apply the oracle. But this is oracle 2, not oracle already. So remember to quote the correct function. Then after that, apply Hadamard to the first n qubits again, same as your second step. Then at last, measure the first n qubits. So if you see all qubits are 0, 0n means you have like 4 zeros, okay, then the function is constant. Otherwise, it's balanced. So you can try to write the code over here. And I'm sure you have the GitHub, so you probably have the solution already. Is it?
Yeah.
Yeah. So try to do it first. And anyone help me in the morning session, you guys got go here and no, don't. 10 minutes. Okay, so let's take 10 minutes for the code. So we'll come back for at 3:40. Press up. So morning, no one go and any. Yeah.
Doesn't it any so we have for the first one the oracle have 2, right? The oracle have
The
two.
first Dosh or Dosh?
The first, I think is
The first one is it?
is it George? Is this George? I think. Yeah, the first one, Dash algorithm. So I'm trying to implement the second one.
Yeah.
The first one we have 2. But
Yeah.
we don't need to do anything to. We just place the oracle in, and then it's just gonna take it, right?
Uh,
For the second one, 5. If we have 5 like that, we just place it the same way.
yeah, you just place it the same way.
It's gonna be
Yeah. If you're not sure, you can always draw the circuit out.
Yeah, because
Yeah.
this one is obvious because you have C naught in the circle and I see it.
Understand.
We try to.
It's going to be just the same.
Okay.
Yeah.
Sure.
Because I defined the oracle also in a way like the 5 qubits, right? So you also have to follow the definition.
So the rest will be always plus minus 1, but the zeros, the whole will always plus. How many times one oracle? So that one time.
No matter how many qubits, no, and qubits also, if you give 100 also 100.
That's a lot of.
Just now you guys got learned about the detailed mathematical answer. I didn't follow. Oh, that one classical you for like half of it. Half of it plus what?
So I'm trying to manage your state. It's because we have one class.
That's why when you need n classical bits, I didn't mention.
Okay.
Yeah, you have to define the system. Yeah. But how many like you can add classical bits to it.
Okay.
I would expect you to only understand what the block of thing. No. Oh, because starting from tomorrow, it doesn't make sense.
Yeah.
You guys. You can understand how it works. It is easier to just understand the logic.
Or in your case, actually, the group quantum suddenly want you. Yeah, quantum field. No, quantum field theory. You learn a little quantum field suddenly want you to find the yeah, quantum gravity. Yes.
It's equivalent from electromagnetic to electronic.
Yes. It's like how we understand how what happened 10,000
And what you what happened
I get it already.
Yeah, kind of.
Well, it's not that.
Is that right?
No.
What result you
No.
get?
So I haven't put just.
No.
No, I'm just looking at it. So you say here. So by applying not an HK, you want to convert all the
QB. This function.
So just the last. Yeah, I think that's what I was going to discuss. N plus one. So
I think there's some time. N plus one should
yeah, okay, makes sense. I thought it was N plus one. 所以这个是我还没跟
这个是concern 我们是因为你的our function as can input and maps it to 0 or 1。
这里有两个
不是这个是新的，这个是 DOS， 这个是 DOS 9.3，然后这个是有两个 input， 所以这个 function 比较 test 它嘛，就是如果这个 function 我是1，可是它可以 int 0或者1，就假设这样有两个 input 0， 然后第二次也 0， 就是你的两个 and 0， 然后你 output 这样就是 constant。
So the last one is
Okay.
do I apply?
the rest defines
Yeah, so we need to apply all pretty much all users, right?
the rest.
Oh, the rest of
Not N plus one, because you already applied.
okay, yeah, yes.
So remember just now you put everything in.
假设我们的 input 我们是两个 input A 跟 B，A 跟 B， 然后你放进这个function里面，你要 output 的是这个 C。OK， 但我们不懂这个是什么，我们不懂，但是我们知道这个 ABC 一定是这样子来，因为它是 B 的。OK， 所以
桌子。
这样子哦。
你的 second
OK， 我们不知道这个我们是我们现在要OK， 就是然后如果今天你放这个0，然后它出来是，然后如果你放0，这个放1，它出来也是0。你放这个1，这个0出来也是0。你放2个1出来也是0，这个我比较不准。就是如果你在四个 qubit， 这样。
一个 A 吧。
对呀。你看一下 input 两个都可以哦，然后 input 两个都是。就是如果你 test A， 你的 input 是这样子，它出来 input 这样子出来，这样子出来，那我们叫 concept。
那这是0，
一个0到这边我们是用的发数学吧不是。
How do I test? 要
我就是
you need to design the problem.
但是你可以开来，你放 and 就类似我们呢在 Qiskit， 是我们现在是。
So how is it?
就是我那个 server 是两个。我明白。是明白。
So like just now we
不用紧，所以你的 input 跟 output， 那你的 input 还要得到一个 function 会 output。因为这个是一个问号。OK， 我们知道我们 input 是两个，就说两个 number 啦，两个数字。
Usually you don't.
然后我们 output 是一个数字。
所以
OK， 这两个数字它的可能性有可能性 combination， 对 form 是原来。
If I change this, like I apply
这样你就 test 0以后。我们不知道，你假设这个 function 是一个 black box 啊，你看不到就是可以掉。
if you change
当你们看错来这个这样子，OK，然后你现在是你要
the reason why
比如说你
you get this particular result is exactly from a mathematical speaking. Show
function 也可以可是我的function 就是有一个朋友是
I also don't understand. I just know the idea. Why?
刚刚在玩什么？
哪一个 side？
刚写讲数学。
有那个就是数学版，现在讲的是电脑版，你要讲的是 desktop。刚刚前面那个是数学版，数学版就比较 complicated， 很 complicated。
可以再看一下那个数学吧。
数学版，
我呢？
还要看那个 slide。
我可以说 but like 你可以按掉，就你去讲那个按掉还会有
可以哦。等下，已经看到时间了，是？
应该是10分钟了吧？讲
可能10分钟吗？可以 show 那个 solution 的，怎么解释啊？
都只是这样，拜拜。
哦，拜拜啊 ！That's all for today. Bye bye.
So that's all. Tomorrow we can show the result.
And the expert talk. All right. So, for now, I will just show the solution for this question. How do you? Eh? Power. Oh.
No.
Then how?
Okay.
Solutions for module 2. Module 2.
No.
Okay. So, okay, so this part is our oracle that we have just defined just now. So for now, we have 4 input qubits. Because as you can see, this oracle is a quantum circuit with 5 qubits. So we basically, it's understandable that we have like number of input qubits is 4, but then when we create a circuit, we have to create a quantum circuit with n plus 1 qubits, because we have total n input qubits and 1 output qubit. So we have total n plus 1 qubits to initiate. Then we'll have n classical bits to store the information. Then we can start by setting the output qubit to 1, okay, the last one, and then we apply Hadamard gates to all qubits. This one is just to flip the qubit. Then after that, the Hadamard gates, I just do it at once. Just put everything as just apply the Hadamard gates to everything. Then we will add the oracle. Then again, apply Hadamard gates to all input qubits. This one is just n, not n plus 1, because for here we are actually including the output qubit. Remember the steps. So for after you add the oracle, you just have to apply the Hadamard gates to the first n qubits only. Then at last, you will measure all input qubits. So you measure the first n input qubits and you store it to the first n classical bits. We have n classical bits, right? So basically, you measure from the n qubits, store it to the n classical bits. Then this is just visualization. You run the job on simulator, analyze the result. So if at last, if you see everything in the array is 0, then it's a constant function, or else it's going to be a balanced function. So in this case, it's a constant function because you get 0, 0, 0, 0 for 1000 times. So it's a constant function. Any questions? Any? No? Okay. So I guess this is the last session for today. So for tomorrow, we'll have Shaw's algorithm in the morning, and in the afternoon, we'll have expert talks by two experts. So that's it for now. Thanks for attending, everyone, and bye.
Yeah, we should take photo because I think
If you end the Zoom, to end.
slide. I don't think so. 13 only.
I'm still at 13.
So how? Yeah, sure. Maybe you want to ask them to on. No. So maybe everyone can just on your camera for a bit or photography session. If possible.
We can go pick one.
怎么样做成 grid 了？
Yeah.
I think it's grid view. Yeah. Gallery or not? It's fine. Yeah.
Okay. No, I don't think they want to.
If they want.
Can everyone open your camera for me? Just for photography session. Yeah, just go in.
Okay. Give the aim, yeah. Yeah, have to revise, stay until the end, have to revise, and then anything that you need to know, you can give the question, tomorrow we back again, okay. So on the camera, everyone come to the phone quick, please,
We must on also. So we have to on how
to do what?
Yeah, on or don't need. Should we?
Thế nào? Này đi sao? Okay, for a second, okay. Very far. You will be feel very blur, but okay.
Yes.
Be take care, No, that's the like. Okay, I'm free. Yes. Everyone go the side on. Okay. We will put some together.
I always try to know, but wow, what is it? Come. Yeah. Hey, Peter, come. Hey,
Yeah.
Try not to block.
You can see the face.
One, two, three, okay, three down, three, okay, done.
Thank you, everyone. Thank you. Okay, see you tomorrow at 9 o'clock. Huh? Okay. And then the workshop, you change the venue to the opposite room, faculty meeting room. The other side, not this room. Right?
Okay. Same building.
Opposite side. Yeah.
Okay. All right.
Faculty meeting room. Okay. Thank you.
Right.
Thank you.
Thank you very much.
See you tomorrow. Yeah.